with the composition operator is a group. Please note that we consider this function bijective because we consider the composition of these functions, and this composition is again a bijective function, okay? And in bijective function we have inverse for each function, okay? So that GLE equal to the set of all f from E to E such that E is linear and so the f is linear and 1 to 1 and onto. These two means f is a bijective, okay? So for any function in GL of E, f is a bijective function, so there exists an inverse from E to E such that f o f inverse equal to f inverse o f equal to identity function on E. And our operation in this group is composition of for function, okay? GLE with the composition operator. In this space we have identity map from E to E by this function rule I of x equal to x, and we know that the identity map is the identity element for this group. IOF equal to FOI equal to F for all F in GLE. For all F in GLE, okay? And for any f in GLE we have the inverse of f from E to E, that we know that the inverse of f is linear and bijective, so this is an element of GLE, and we have these equalities so that any element in GLE have an inverse with respect to this operation, with respect to composition as a binary operation. Definition: any homomorphic such GLE is called a representation, because we know that these two are groups. Okay, G is a group and this is a group. Let me write. For example, if we consider a group G with the binary operation star, row from G to GLE of E or GL of E with the composition must have qualities that for any, let me write, for any X and Y in G, row of X star Y equal to row of X or row of Y. Okay, because the binary operation in this group is composition. So row is a homomorphism, a group homomorphism. Okay, any homomorphism from row, such as row from G to GLE, is called a representation on G. If T from X to Y is linear, then usually instead T of X is written Tx. And if row from G to GLE is a representation, we know that if G belongs to E, row of G must be belong to GLE, so that row of G is a function from E to E that is linear and bijective. Row of G is a function from E to E that is linear and bijective function. So for every V in E, row G of V is an element of E. Let me write. Row G of E is an element of E. Recall that? If E is a vector space over curve with base, for example, E1 up to the En, and E prime is another vector space with the base E1 prime up to En prime, then for each linear functions such as T from X to Y, if T of EI equal to this linear combination of this base, because we know that T of EI is an element of Y and this is a base for Y, so that T of EI must be right as an linear combination of these elements. Now if we consider this matrix. This is M times N matrix. Then for each X in X, because in E, because we know that any element of E is a linear sorry, every element of E is a linear combination of this base. Okay, so that instead of Tx we can write this matrix multiplied by this vector, and for any linear from E to E prime we have a matrix M times N matrix, and vice versa. Please note that this E prime is not the dual. So we can write this by another notation, okay? Such as F. And this T is from E to F. Function linear function such as T from E to F, okay? And you note this observation that any linear function is corresponds with a matrix, okay? Now, please see this example. Let G car E, G car of G equal to the set of all F from G to K, such that F is a function. Then this is a vector space. It is very trivial. K is our scalar field, okay? K equal to real numbers or complex numbers, okay? It is very trivial that this is a linear space or vector space by this ordinary operation f1 plus f2 equal to this, and alpha f of x equal to this. Please note that if we consider for example real numbers, f1 of x is a real number and f2 of x is a real number, so that this is a real number, and also this. And if we consider this complex number, these two are complex number. Please note that in this definition, f1 and f2 are in Ck of G x is an element of G and alpha must be belong to K. If this function maps to K, this alpha, this scalar must consider from K. If K equal real numbers, this alpha is real numbers, and if K equal to complex number, this alpha must consider as an complex number. Okay. Now we can consider this as our vector space and define a representation. In any f in ck of G and for any x in G, define equal to f of xy. Please note that we must consider G from this group. Okay, so rho G of G is an element of GL of E. Rho G of G is an element of this group GL of E, so that rho G of G is a function from this vector space to itself. So rho G of G must be act on function in this linear space. Function in this linear space, so that we write, please note that we write rho G of G of F, rho G of G of F for any F in ck of G. Now rho G of G of F is an element of ck of G, so that this is the function from G to K, and this can be act on all element in our group G. Rho G of G of F can be act on elements in G, because rho G of G of F is an element of this vector space, and this vector space is the set of all linear function from G to K. The set of all function such as F from G to K. Okay. And if F belongs to ck of G, rho G of G of F must be belong to this space or this space, so that rho G of G of F is a function from G to K, from G to K. Now we define rho G of G of F for any x in G equal to f of xy, that is an xg, and this is a well defined definition because xg is an element of G, because x an element of G and also G is an element of G, and xg must be belong to G. So this f can be act because f itself is a function from G to K, and this value maps to K, so that this is a scalar numbers. Scalar numbers. And so this is a well-defined function from G to GL of secant G. Dear students, do you have my voice? No, we see that for any G and H in G, rho G of GH equal to rho G of GO rho G of H. Because for any F in secant of G and for any X in G, by the definition of this representation, we have rho G of G or rho G of H of F of X equal to rho G of G of rho G of H of F and of X. And rho G of any function such as H, if you denoted this by H, for example, for T, for example, this is your T, okay? Rho G of G of T of X equal to T of XG, okay? Rho G of any F of X equal to F of XG. This F must be replaced by this function T, okay? T of XG, and it is equal to F of GH multiplied by H. On the other hand, so that this is the result of rho G of GO, rho G of H of F of X. On the other hand, for any F in secant of G, on the other hand, rho G of GH of F of X equal to this, because if we consider this function or this element of G is equal to F of X multiplied by GH, and this is the next line. So for any F in secant of G, rho G of G or rho G of H of F equal to rho G of GH of F is hold for all F, so that these two functions must be equal, and so this is a representation, and we have this equality. Now we recall this representation as left regular representation, lambda G from G to GL of secant of G by this function rule for any F in secant of G and for any G and X in G, lambda G of F of X equal to F of the inverse of G multiplied by X. this is similar to the previous representation, but we use the inverse of G in this definition. Lambda G is a representation on G that is called a left regular representation. And we have another example. Let G be a group, then row from G times G to GL of this E by this function rule. Row of G and H, row must be act on this product space G and H such that G and H are element in G. Row of G and H of any F in this and of X equal to F of the inverse of G multiplied by X multiplied by G. We define this, okay? This is the representation on G times G. Please note that this the homomorphousness of this representation okay. And so we must check that this is a representation, but this is easy and similar to the previous example. Please write this for yourself that this row is a homomorphism from this group to this group, okay? And please note that if G for example with this operation is a group, then G times G with a star prime, for example, is a group, and we know this, and this is a star prime for any, for example, G1 H1 and G2 H2 in G times G, G1 H1 S star prime, G2 H2 equal to G1 G2 S star H1 H2, okay? and this is very trivial that this is a group, because you have identity map E and E, because for any G and H in G times G, G and H star prime E and E, this is the identity element of G, okay, equal to GE or G star E and H star E, and this is equal to GH, and similarly EE star prime GH equal to GH, and element have every element such as G and H in G times G. We see that G inverse and H inverse is an element of G times G, and we have these equalities. This equal G star the inverse of G and H star inverse of H, and this is equal to E and E, or identity map. And the opposite direction is also holds, so that any element have an inverse, and it is very easy that this operation star is associated, so that G times G and star prime is a group, okay, is a group. Now we have this representation row, so that we see that row of G and H star prime, or G1 H1 G2 H2 of f of x equal to row of G1 star G2 and H1 star H2 of f of x, and this is equal by this function rules, okay, G1 star G2 inverse f of this, okay, f of this, f of this multiplied by x multiplied by the inverse of this element H1 star H2 inverse, and this is equal to f of this is G2 inverse star G1 inverse multiplied by x, and we must write a star. This is H2 inverse star H1 inverse, okay, the inverse of H1. And this is equal to G2 G1 H2 H1. Let me now sorry, this is H, not this is H, now the inverse of H. Okay, this is H, so that we must write itself, and so this is H1 star H2, H1 H2. Okay, now we see that this is equal to rho of G1 and H1 of rho of G2 of f of x. This is very clear because rho of G2 and H2 of f of x equal to f of G2 x and S star H2. Okay, and so rho of G1 and H1 of this equal to rho of G1 and H1 of this, so that this G1 must be act, the inverse of G1 must be act in the left hand, and H1 must be act in the right hand. So this is a representation theorem. This is another example by this group. Note that if G1 and G2 are groups and T from G1 to G2 is a homomorphism, then T is injective 1 to 1 if and only if the kernel of T equal to E. This is very trivial, and note that by definition kernel of T is all x is 1, T of x equal to the identity element of G2, identity element in G2. So that the identity element of G1 is always in the kernel of T, because T of EG1 equal to E of G2. And for this T is injective if and only if the kernel of T equal to this. We see that if we assume that T is injective, then for any x in the kernel of T, T of x equal to E of G2, the identity element of G2. But we know that E of G2 equal to T of EG1. So that T of x equal to T of EG1. But T is injective by our assumption, so EG1 must be equal to x. So any x in the kernel of T is the identity element, and we have this equality. For the converse, if the kernel of T equal to this singleton, and we have T of x equal to T of y, Tx that the inverse of Ty equal to Eg2, the inverse of this. But T is linear, so that this equal to T of x multiplied by the inverse of y. And this shows that this element is in the kernel of T. But we assume that the kernel of T equal to E, so that this must be equal to E. And if we multiply y in both sides of this equality, x must be equal to y, and so T must be a one-to-one or injective function. T is injective if and only if the kernel of T equal to the identity element. And also we have this example. Dear students, for the representation theorem and theory, I specifies another book for you, okay? Let me write. سأقدم الله آخر لمحتوى جديد, okay, for representation theorem. Do you understand, dear students? And we have this example again for the group G by this binary operation. For example, we have the following representation. Row from G to GL of G is isometrically isomorphism with GL1, and this is equal to the set of all non-zero elements in 0. So this G must be real numbers, okay? This is real numbers. Real numbers. And also all of these are real numbers. Or complex number. Oh, sorry, this is not G, it's complex numbers. Okay, these are complex numbers, okay? I read this G. This is complex numbers, and these are correct. And you know that complex numbers is a vector space, so that our group is complex number and our vector space E is complex numbers. But we know that GL of E, the set of all function the set of all continuous and bijective function from C to C equal to the set of all one-to-one matrix by complex variation, okay? Because we know that GL of C equal to the set of all F from C to C such that F is linear and bijective, okay? Linear and bijective. So that F is an element of GL of C if and only if there exists a non-zero element in complex numbers such that F has this function rules. We know that any bijective linear maps from C to C must have this definition by these function rules. For any x, f of x equal to alpha x, and this is very easy to prove. So that for any f we have a complex number, and this complex number is one-to-one matrix, so that we have this corresponding any linear and bijective function from C to C corresponding to a complex number, a non-zero complex number, and any non-zero complex numbers is in a corresponding to a matrix, non-zero matrix, okay? And the set of all non-zero complex number that we denoted by this is isometrically isomorphous with GL of C. Let me recall again for you that for representation we must have a linear space or a vector space such as E and we must consider GL of E the set of all linear and bijective functions from E to E, that we know that this is a group with the composition as binary operation. Now a representation on G is a group homomorphism from G to this group, from our group G to this group GL of E. Any homomorphism such as rho from G to G is called a representation on G. Okay. And if we consider this as a vector space, ck of G equal to the set of all f from G to k such that f is a function, only a function, then we see that this is a vector space, so we can consider this as our vector space E, or vector space E, and define a representation by this notation rho G from G to GL of E by this function rules. Rho G of f of x equal to f of x G. Okay, and also we see the left regular representation on group G lambda G from G to GL of E by this function rules. Lambda G of f of G equal to f of the inverse of G multiplied by x. Okay, then lambda G is a representation on G that is called a left regular representation, and we see this definition rho from G times G to GL of ck of G by this function rule, that we see that this is a representation. I write this, but let me complete this for you. We see that this equal to this. Okay, on the other hand, rho of G1 and H1 O rho of G2 and G2 of f of x equal G G1 rho of G2 and H2 of F of X. So if we consider this is equal to you must write this rho of G2 H2 of F of the inverse of G1 A star X A star H1. Okay. Now for this is equal to F of the inverse of G2 A star this A star this. Okay, this is all element in X, for example this G1 inverse A star X A star H1. Okay, this must write, but this G2 inverse must be act in left side, and in the right side we must have H2, and this is exactly equal to this. Okay, so we see that rho of G1 and H1 A star prime G2 and H2 of F of X equal to this, and rho of G1 H1 or rho of G2 H2 of F of X equal to this again, so that these two are the same. And so rho of G1 H1 A star prime G2 H1 G2 H2, and this is the proof of this example, and we have this easy fact. And finally this example. Okay, let me continue in the next session. Dear students, do you have any questions? Okay, goodbye for now, the operator theory class. Okay, after 50 minutes. Okay, goodbye.